In this lecture, we'll be talking about the Gaussian elimination method, which is a direct consequence of the raw elementary operations that we did, whether on the equations of the linear systems or on the matrix, augmented matrix rows. And you will see later on that from a purely programming point of view, if you want to use computers to find the solutions to a system, this playing with the matrix is a far more convenient than playing with the equations and the system. So we'll be talking about this more throughout, and the power behind using matrices. This technique was named after the German mathematician Gauss, who lived in the 1800s. But the technique itself was known for a very long time. For example, it was known earlier on to the Chinese mathematicians. In any case, so as I said before, this technique will help us understand some of the inner working of the matrices. You will see why I'm talking about, of course, here some when you go to the abstract linear algebra, you will find out, for example, that the concept of rank and nullity and connection to the dimension is so abstract, while this technique, at least in the final dimensional case for matrices, comes very natural and very simple and very easy. Okay, so for us, we'll focus mostly on still solving linear systems. So of course, either linear systems or systems of linear equations. That's fine. Here, remember that we talked about the elementary operations on the rows of the augmented matrix. So we will work with the augmented matrix. Okay, so remember that the augmented matrix is something like this, where you have columns and rows, and this part here has the coefficients of the system, okay, the coefficients, while this part here, this column, the last one, okay, is the non-homogeneous terms, okay, in your linear equations. Okay, so sometimes people will call this one here the coefficient matrix associated to the system. Okay, if the system is homogeneous, meaning that the last column is only zeros, then obviously we have what we call the trivial solution, which is the 0, 0, 0, 0. Okay, it is a solution, and therefore homogeneous systems are consistent. Okay, so that's the only difference between non-homogeneous and homogeneous linear systems, is that one may be inconsistent, no solutions, and one is always consistent. Okay, so in this case, there is no need for us to use the augmented matrix. We can only play with the coefficient matrix. But we'll see later on when we go to the matrix representation of a system that the coefficient matrix is vital somehow for our study here. So remember, I'm just recalling here that what we said is that when we use the elementary operations, I don't want to say row operations, though I mean row operations on the matrix, but elementary operations can be done on the system as well. It doesn't have to be, we can work only with the system, okay, instead of working with the matrix. Okay, that's possible as well. So these elementary operations, which consist in what? Either you interchange two equations, or you multiply equation by a non-zero number, or you can take an equation and add to it a number times another equation. So these are elementary operations, and the goal is, when you start with your initial system, okay, and you apply these elementary operations, you end up into a new system. And this new system is equivalent to the initial system in what sense? In the sense that they do have the same solutions. So if the goal is to find the solutions, okay, then you can basically work with the initial system, or you can work with the new system. So what is the advantage of the new system? The advantage of the new system is that it's easy to solve. So there are two types, okay? So first, let me just talk about the augmented matrix here. And what happened is you start with the original one. Okay, this is your original augmented matrix. And once you do the elementary row operations, you end up in the new one, in the new one now. Okay, and there are two steps. Okay, two steps. So the first step is called the forward elimination, okay? And the second one is the back elimination, okay? So you go down and you go up. So let's of course there are technical names for that, but let me explain exactly. So what you do, once you do these elementary operations, you will find out, so again, it's like this. And what happened is in the first, when you go forward elimination down, okay, so you end up, this is, okay, plenty of zeros. We call it a triangular matrix, okay, plenty of zeros, okay. And this putting some, of course, we'll see this in some examples. This system, the new system in this form, is a lot easier to play with, to solve, to decide if it's consistent, inconsistent, if you have only one solution or infinitely many solutions. But when you go up, when you continue, okay, you don't have to, you can do it here. And you can find solutions here. With little bit of work, you start with the last ones and you start going up to find all of them. Back substitution, and you find all of them. But here, if you continue even playing with the raw elementary operations, you can almost like reduce, okay, your augmented matrix into one that gives you the solutions, okay, if any, of course. You can almost see it in the first move when you go down in the forward elimination. You can see if you are consistent or not. So I will give you an example of this and you will see what I'm talking about, okay? So basically, this is what happened. Two steps in dealing with this. So let's take an example, okay? Example. And let us solve the linear system 2x plus y minus z equals 8 minus 3x minus y plus 2z equal minus 11 minus 2x plus y plus 2z equals minus 3. So again, to appreciate the power behind this technique, I want you to look at the system for a second. It's so hard, even though in the examples that we use from a pedagogical point of view, we take simple examples. But in real life, when you are dealing with engineering or economics or other areas of applied science, and you are using systems, they are large first, the numbers are not nice. You don't see 2, 3, minus 2, minus like the example I did in the economics with the investing in bond and stocks, and you have numbers that are not nice looking. So the solutions can be also not nice, okay? So the technique itself is very beautiful. It's very simple. And sometimes the student can be faster than the instructors, because this technique, the student can see the numbers and how to handle them and how to play with them and which operation to do. I'm talking about the raw elementary operations, which one to do. Sometimes I get surprised to see that my students are coming up with some amazing, faster operations than the ones I'm offering. So let's first come up with the augmented matrix, as we said. Okay. Okay. So what do we have? We have two, the coefficients 1, minus 1, minus 3, minus 1, 2, minus 2, 1, and 2. So these are the coefficients, or the coefficient matrix of the system. And then we put in the non-homogeneous terms, 8 minus 11 minus 3. Okay? So let us do the following. So first, what are the elementary operations we're going to do? So I'm going to take the second line. So let me call these ones, for any matrix, I will call these ones line 1, line 2, line 3. I have 3 rows, 3 lines, okay? So let's take L2. So I will preserve L1, and I'll take L2. Let us remove the 2 into 1, so I divide by half, and then multiply by 3 to have minus 3. So I will take minus 3 half L1. Okay? So what happened when I do this? So first, hold on, let me put it under it. I will write this here, and the result I will put it here. So I will preserve 1 minus 1, 8. And now what happened? So I'm taking L2, and I'm going to replace L2 by the second line minus 3 half times the first one. Not minus, sorry, because it's already minus. So I'm going to take plus. Okay, so what's going to happen? 3 half times 2, that's 3. But you have minus 3 plus 3, 0. So we will have 0. That was the idea behind it, okay? So the next one will be what? Minus 1 plus 3 half, 1 half. Okay? So here you have to be careful about the algebra. 2 minus 3 half plus 1 half. And minus 11 plus 3 half times 8, that's 12. This will give me plus 12 minus 11, 1. Okay? So I can now keep the third line and start working on the third line to remove the minus 2 from the third line, the first number. And instead of doing this, I'm going to do it in one shot, just to save me some time. So I'm going to take, look, we have minus 2 and we have 2 on the first line. So I'm just going to add them. So I'm going to do L3 plus L1. So 2 row elementary operations in one shot, just to save me some time, okay? So minus 2 plus 2, 0. 1 plus 1, 2. 2 minus 1, 1. And minus 3 plus 8, 5. Okay, so I use the fact what? So here, let me explain something very important. So this 2 here played a role. The fact that is not 0, that's how I was able, the first number, that was I was able to have underwrite the zeros. So remember, what did we say? We say that we call this technique moving downward. So I'm moving downward, okay? Or as the technical name, as they call it, the forward elimination. But you see, this is the idea. Every time that you have a number like this, and you can go down and you eliminate the ones under it, okay? Eliminates the zeros under it. Okay, so now I could have made, by the way, the 2 equal to 1 by multiplying by 1 half, okay? I can always make it equal to 1, okay? So here, for example, you see 1 half, 1 half, and 1. I don't like fractions. Let's multiply by 2 for the sake of argument. So here, we're going to multiply by L2. We're going to take 2 times L2. L2 being the second line, of course. So what would be the next matrix? 2, 1, minus 1, 8. And 0, 1, 1, 2, 0, 2, 1, 8. Okay, so now that I have 1 in the second, the first is a 1, I'm gonna take now L3 minus 2 L2 to remove the 2 in the third, the first 2 that we have on the third row. So what do we get? We get 2, 1 minus 1, 8, 0, 1, 1, 2, 2 minus 2, 0, 1 minus 2, minus 1, and 8 minus 4. 2 times 2 is 4. Okay? Now, if you want to have, if you want to have 1, 1, 1, so let's multiply the first by 1/2, L1, and let's multiply the third one by -1. So now what happened? 1, 1/2, minus 1/2, 4, 0, 1, 1, 0, 0, 1, minus 4. So I don't have to do that, but so as you can see, look at the shape of this matrix. It's very, very interesting. So first of all, the first non-zero is a 1. You can make it a 1, even if you, like, for example, here is -1 in the one before. Okay, so here you had the 2 and you had the -1. You can work with it, that's not an issue. But if you want to have a 1, it's simple. You just multiply the row by a number and you get, you know, the one that you want. So let's have the number is 1. So you see, you have a number, the first one on every row is a 1. And look at under it. So you have 1, yeah, 1 and 1. And look at under the ones. What do you see? You see that you have zeros. Okay, so this matrix has a name. So it's triangular. I'm talking coefficient matrix, and the coefficient matrix is triangular. It's basically upper triangular. In other words, the zeros are under what's known as the diagonal, and we'll talk about it for square matrices. But these numbers that I put in a circle, they have a name. We call them the leading numbers or coefficients, because they become coefficients for the new system. Okay, so if you are in this form, this is known as a row echelon form. Okay, so this row echelon form here, what does it say if you look at the new system? Now let's go to the system. So the first equation is going to be x plus 1/2 minus y minus 1/2 z equal 4, y plus z equal 2, and z equal -4. So you see, look at the last equation. Z equal what? -4. So you found z. So what you do, you can go up. Maybe I did a mistake. Yeah, most likely I did a mistake. Hold on, let me see. What did I do here? 2. Okay, so was it an 8? And what about this one here? I think I have a problem. Algebra, huh? So -2. What did I do? L3 plus L1. -2 plus 1. Okay, so you see, here is my mistake. 1 plus 1 is 2. 2 minus 1 is 1. Here is my mistake. 8 minus 3, that's a 5. So let's put 5. Okay, so here it is a 5. And now what did we do? We took the L3 minus 2L2. Okay, so it's gonna be 5 minus 4, that's 1. And therefore, so it should be here when we multiply by -1. Okay, great. So now z is equal to what? -1. So once we have z equal to 1, we can go to the second line and find y, and we can go to the first line and find x. You can do that, okay? So it's simpler. Now what about if we want to go backward? So this is downward, gave me the row echelon form, okay? What about if I keep going with row elementary operations and go up? I can get rid for all the numbers that you see there in red. I can get rid of the numbers above them and have zeros. Okay, so let's do it. In other words, we can push the elementary the elementary row operations or row elementary operations and keep going. So now let us get rid of the 1 first. Okay, so we're gonna take here, I'm gonna take L2 minus L3. Okay, so we have 0, 0, 1 minus 1 because we found that z, and now we go. So it's gonna be 0, 1 minus 0, 1, 1 minus 1, 0, 2 minus 1 plus 1, 3. Okay, and let us get rid of the minus 1/2. So how do I do that? I take 1/2 times L3 plus L1. Yeah, so it's gonna be what? 1 plus 0, 1, 1/2 plus 0, 1/2, and minus 1/2 plus 1/2 because it's gonna be 1/2 times 1, 0, and then 4 plus minus 1/2. So 4 minus 1/2 is gonna give me what? 7/2. Okay, so now let us get rid of the half above 1. So what do we do? So we have, and by the way, at this stage you have y. Y is equal to 3, z is equal to minus 1, and y is equal to 3. So we go 0, 0, 1, minus 1, 0, 1, 0, 3. And now what do? We take L1 minus 1/2 times L2. So we get 1 minus 0, 1, 1/2 minus 1/2, 0, 0 minus 0, 0, 7/2 minus 3/2, 4/2, 2. Okay, so look at now this one. This is known as the reduced row echelon form. It's better than the row echelon form. Why? Because this one gives you, so what's the system now? Look at the system now. Okay, x equals 2, y equals 3, and z equal minus 1. So it gives you what? The solution. The other one, you have to do a back substitution to be able to do that. Okay, to be able to do that. So next, let's just put a remark here. Okay, remark. Okay, so some examples of row echelon form. Row echelon form. So keep in mind some examples. You have the first non-zero can be any number in general, but you can have also 1 by multiplying by a constant and reduce it to 1. So let's say, for example, you have 1. Once you have 1, here it doesn't matter what you have. Okay, but under the 1 you must have zeros. Okay, so assume you have a 0 here and then a 1. Okay, here it doesn't matter what you have. Okay, but then you cannot have a number. Let's say, for example, you have a number here that's not 0. No, you have to interchange. Okay, so you will never, the leading term, all the numbers all the way to the leading term, the next leading term has to be a little bit farther to the right. So it has to be zeros here, and then here you have what? Zeros. Whenever you have a leading term, and you can have, of course, like 1 here, okay, and then you can have zeros, okay, you can have zeros under it, okay. So the 0 rows can be there, it doesn't have to be. So this is the row echelon form. The reduced echelon form above the leading, so the leading one, so you have 1 0 0 0 star 0 0 0. Above this 1 here, which is the leading term, you need to have a 0, okay, 0 0, and then you have a 1 0 0 0, and then you have star 0 0, and then here star. So it's always now the leading term. Once you have the leading term or the leading coefficient, the leading number above it, it has to be 0. So this is the reduced echelon form and row echelon form. Okay, so let us now go to in general. So what happened, remark here, or interpretation, or solutions. What can you say? Solutions to the system. Okay, so once you do the row elementary operations, you start with your augmented matrix. Okay, here we are from the system, and you do your row elementary operations. So whether you do down or up, it doesn't matter. So either you have the row echelon form or the reduced row echelon form. Okay, fine. Let's go down to the row echelon form. Not the reduced one, just going down. So you have a matrix like this. So at the bottom, you're going to have the zeros, okay? Zero, if any, of course. Of course, I'm assuming, like the example we just did, we didn't have a row of zeros. But what if you have a row of zeros? Okay, so you look at the last number. Okay, what if the last number here, okay, is not 0? So what are the equation now? Look at the equation in the system. You're going to have 0 times x1, 0 times x2, all the way to 0 times xn, equal that number, okay? Meaning what? You have 0 equal this number, which is not 0. So the system is inconsistent. You are not going to have. So in this case, you can conclude that the system is inconsistent. No solutions. So you see, when we go forward with these row elementary operations on the augmented matrix, if we see that happens, stop. It means that the system is inconsistent. But keep in mind, you saw it. It's very easy to do an algebra mistake. It's very easy. So make sure that your calculations are done in a way that when you claim it's inconsistent, it's really inconsistent, okay? Okay, so otherwise what happened? Okay? Otherwise, what you have, in fact, is, so you may have a row of zeros, you may not have a row of zeros. Assume you have row of zeros. So what you have here is zeros and zeros. So all these rows of zeros, you put them at the bottom. Okay, so you look at now the non-zero rows. Okay, non-zero rows. The block here, this block here, all of it is a bunch of zeros. Excellent. Now look at the rows which are non-zero. So these are the non-zero rows. Okay, count them. So R is equal to the number of the non-zero rows. Of course, for what? For the echelon form, the row echelon form. Just going forward, I can get this number as soon as I'm going down. I'm not talking about the reduced echelon form. Okay, so this R is amazing. Okay, it's called the rank of the matrix, but anyway, is amazing. Okay, it's an amazing number. So that's what I was talking about, how the inner working of a matrix. So this number, remember, every non-zero rows, how does it start? With some zeros, and then you hit what? Number 1. The leading number is 1. Okay, great. So these R, first of all, obviously is gonna be less than the number of rows, which is equal to m, the number of equations. But you see, look at now the columns. What is the first number of that R? 1. And you will never have 2 rows in the echelon form that they start with 1 at the same position. No way. Once you have a leading number 1, okay, under it is a bunch of zeros. So in fact, from this comment, we know that R, because the columns are, you see, the columns of the Augmented matrix of the coefficient part are exactly the number of what? Of unknowns. Okay, so R in fact is also less than the number of unknowns. It's really amazing, which is n. Okay, so this R is less than the number of rows, and R is also the less or equal than the number of unknowns. And what's amazing is that if R, we'll see on an example, if R is equal to the number of unknowns, it means you can find them all. And in this case, we only have one solution. Interesting. If R is less than n, the number of unknowns, then some unknowns will be floating. You cannot find them. Some you can find them, but some are floating. And what we do, we assign parameters to them and find the other ones. That's how we will do it. We'll see it on an example. And in this case, once you assign a parameter, we have tons of solutions. We have infinitely many solutions. Okay, so once you go forward elimination, once you go downward with the row elementary operations, you can see once you reach your row echelon form and you stop, then there you can decide inconsistent, consistent. 2, you can decide whether you have one solution or infinitely many solutions. Interesting, huh? Okay, so let's take an example now. Let us take an example to illustrate what we just said, okay? Solve the system x plus y plus 4z equal 4, 2x plus y plus 9z equal 5, x plus 5z equals 1. So again, as I said, I always really get amazed at how from looking at the system, the initial system, is so hard to guess what's going on in terms of consistency, inconsistency, and so on and so forth. Okay, so let's start with the augmented matrix. One, 1, 4, 4, 2, 1, 9, 5, 1, 0, 5, 1. So since we have 1 on the first row, the first, that will be my leading term. So now we want to eliminate under 1, which is 2 and 1. Let's eliminate them. So what are the operations we're going to take? We're going to take L2 minus 2L1 and L3 minus L1. Okay, so we get what? 1, 1, 4, 4. 2 minus 2, 0. 1 minus 2, minus 1. 9 minus 8, 1. 5 minus 8, minus 3. And then we have 1 minus 1, 0. 0 minus 1, minus 1. 5 minus 4, 1. 1 minus 4, minus 3. Okay, so pay attention now. Look at the second row and the third row. They are the same. So I'm just going to take, I'm going to multiply the second row by minus. And I'm going to do L3 minus L2. So what do I get? I will get 1, 1, 4, 4, 0, 1 minus 1, 3, and 0, 0, 0, 0. Okay, we're lucky that we have a 0, so this system here is consistent. But what if we found, for example, if we found here a 2, okay, then we can claim it's inconsistent and stop. Okay, so the system, the original system, does not have what? A solution. So here we have a 0. Okay, so what's R? Okay, it's obvious from the, that's it, we're done with the row echelon form. As you can see, here are your leading, okay, and under them you have zeros, and they are equal to 1. I mean, it doesn't have to be equal to 1. In some books, they don't need the leading term to be equal to 1, but that's fine. So in this case, we're done with the echelon form. So let's look at now the number of, R, the number of non-zero is equal to 2, less than 3. So there are 3 unknowns, and we have R is equal to 2. Okay, so clearly, okay, one unknown will float. One unknown, 2 can be found, and 1 will be floating. So here, obviously, what we are gonna do, let's take the system. So we can still do the roid. So we have, as I said here, we have infinitely many solutions. Okay, so let's look at the system. I mean, I can still, for example, do one more if I want to have the reduced one. Okay, so let's do the reduced one. Okay, 0, 0, 0 for the sake of, I don't need it, but okay, to finish the job I could have worked with the this augmented matrix. But anyway, so 0, 1, minus 1, 3, and let's take above it this one here out, okay, because above a leading term. So we're gonna take L1 minus L2. So 1 minus 0, 1 minus 1, 0, 4 minus 1, 5, 4 minus 3, 1. Okay, so now what is the system now? The new system. This is the reduced echelon form. So what is the new system? So the new system will be X. You can use X1, X2, X3, or you can use X, Y, Z. X plus, of course, it depends on what they gave you at the beginning. Sorry. They give us X, Y, Z, so we have to work with X, Y, Z. Sorry. 5Z equals to 1. Y minus Z equals to 3, and there is no need for 0 equals 0. Okay, so now we set the parameter is Z. We let it float. Okay, it's a parameter, which means any number. It can be any number. So in this case, X will be 1 minus 5Z, 5T. Y will be Z plus 3 or 3 plus Z. And finally, Z is equal to T. Okay, so as you can see, you take values for T. T is a parameter. You can take T equals 0. You will find 1, 3, 0. And you can take T equal 1, which gives you minus 2, 4, and 1. So here, this form here, all solutions are given by, so is a triple X, Y, Z equal to what? 1 minus 5T, 3 plus T, and T, where T is an arbitrary number, where T is an arbitrary number. So this form, this general form that gives you all of them, we call this a general solution. So what you see here so this is known as general solution. Okay, so this happens if you have plenty of solutions in the linear system and you have one form that gives you all the solutions. So let us now finish by what are the things that we learned. Okay, I like to do that. So what are the new concepts? Okay, so we have number 1. So of course, number 1 and 2, we saw them before, but let me emphasize them again. So we have the row echelon form. 2, this is when you go down. Okay, when you go up, you get the reduced row echelon form. Now what's new today? Oh no, sorry, still we saw them before, but again it is emphasized here: consistent and inconsistent systems. Okay, and very important, the number R, the number R, and 5, the general solution.